This video demonstrates a new adaptive control algorithm called TRAC, which stands for Trust Region Reflective Adaptive Controller. The purpose of TRAC is to eliminate the impact of any disturbance acting on a control system resulting from a change in the plant parameters by automatically adjusting the feedback gains. This adaptive process is accomplished by extracting the poles from the actual output of the system and solving an optimization problem that recalculates the gains in a way to absorb the disturbance and leave the output unaffected. The following demonstration shows a sample application of TRAC to the position control of a mass spring damper system with a control law consisting of a full state feedback and a PI controller that eliminates the steady state error. Originally, when the plant is actuated with a step input, the gains are tuned such that the actual output of the system, which is represented by the blue plot, perfectly tracks the desired output represented by the squared gray plot. However, for a given variation in the plant parameter, such as the spring constant, the actual output starts to miss the desired output in the absence of any automatic adaptation in the feedback gains, that is, with TRAC off. This behavior can equally happen as a result of a change in the damping coefficient, as well as a change in the mass, or a combination of all three. However, if TRAC is turned on, the change in the output signal resulting from a change in the plant parameters will be completely absorbed by TRAC via an automatic retuning of the gains, as can be seen in these plots for gains K1, K2, and K3. This adaptation can be carried online as long as TRAC remains on, thereby preventing the leakage of any parametric disturbance toward the output signal. Note that in the top graph, the red plot represents the uncompensated response, or the response of the system if TRAC was off, and that the blue plot represents the actual response corrected by TRAC to eliminate the impact of the disturbance. With this comparison, one can easily see how the actual output stays in line with the desired output when TRAC is on, even in the presence of large parametric uncertainties. A last point to note about TRAC is the number of iterations that the algorithm performs in the background, which is visualized by this slider. This number is a direct function of the amount of disturbance that is allowed to leak toward the compensated output. For example, if some disturbance leakage is tolerated by turning this knob, then one can see how the actual output will slightly start to miss the desired output at the benefit of making the algorithm converge faster. However, if this tolerance is reset back to 0, meaning no leakage, then TRAC will automatically retune the gains in order to eliminate any tracking error with the desired output. This leads us to the conclusion that TRAC offers significant advantages to control systems that are subject to parametric uncertainties or inaccuracies in the plant model, and whereby a time-varying system can be automatically tuned to exhibit a time-invariant response.